Our project name is Inductor coupled by converter to enhance voltage gain in burst mode, guided by Mrs.S.Meenakshi, presented by Divya.P, Sowmya.G and Hemalatha.N. Content: Objective: Drawbacks of the existing system, proposed system, block diagram, circuit diagram, modes of operation, voltage gain comparison, simulation model, simulation output, advantage of proposed system, software requirements, hardware requirements, conclusion, reference. Abstracts. The importance of voltage gain enhancement or voltage boosting is required in many precision applications. A novel voltage boosting converter is proposed which uses a charge pump and a coupled inductor in KY converter. It is a voltage setup converter. It is operated as a buck boost converter combined with synchronous rectification, that is, by replacing diodes with MOSFET switches. The MOSFET switches at high frequency is used to control the output voltage, and it also reduces conduction losses. The corresponding voltage gain is greater than that of the existing step-up converter, and output is a non-pulsating by combination of KY and buck boost converters. Introduction. The converter combines one KY converter, one traditional synchronously rectified buck boost converter, and one coupled inductor with turns ratio, which is used to improve the voltage gain. Therefore, the voltage gain is higher than that of the converter and can be determined by adjusting both the duty cycle and the turns ratio. Moreover, the duty cycle and the turns ratio are independent, which means that tuning the duty cycle does not affect the turns ratio and vice versa. In addition, the proposed setup converter has no floating output and has an output inductor, hence the output current is non-pulsating. Furthermore, part of the leakage inductance energy can be recycled to the output capacitor of the SR buck boost converter. In this paper, a detailed description along with some experimental results is given to provide the effectiveness of the proposed converter. Objective: to improve the voltage gain of buck boost converter, to reduce number of switches, to use the buck boost and KY converter in an efficient way, to reduce amount of ripples in output voltage. Existing system. High voltage conversion converters play an important role in boosting the low output voltages. In existing system, the conversion is not efficient. Output gain are low when compared to proposed converter. Drawbacks of existing system. The output current is pulsating. Output voltages ripple tends to be large. Voltage gain is not high. Proposed system includes the combination of KY and buck boost converter with an additional coupled inductor. Coupled inductor provides non-pulsating output. This is a block diagram of a project which contains the DC source, KY converter, load, driving circuit, PIC microcontroller. This is a circuit diagram of a project. The explanation for the aforementioned circuit diagrams are as follows. S1, S2 are MOSFET switches. NP, number of windings in primary side. NS, number of windings in secondary side. C1, energy transferring capacitor. C2, charge pump capacitor. D1, diode. LO, output inductor. CO, output capacitor. RO, load. BI, input source. Basic operating principles. The output inductor LO is always positive. The dead times between the two MOSFET switches are omitted. The MOSFET switches and the diodes are assumed to be ideal components. The values of all the capacitors are large enough such that the voltages across them are kept constant at some values. The magnitude of the switching ripple is negligible. Mode of operation of our project. In mode 1, S1 off and S2 is on. Voltage across NP is equal to source voltage. Voltage is induced across NS. C2 charges. The output can be given as Vi plus Vc1, Vns plus Vlo. Mode 2. S2 off, S1 on. D1 reverse biased. Voltage across NP is less than the supply voltage. C2 discharges. The V output can be given as V input plus Vc2 plus Vlo. The voltage gain derivation is as follows. This is the continuation of the voltage gain derivation. This chart shows the voltage gain comparison of various converters. The voltage gain calculation for proposed converter. At a constant input 12 volt and the turns ratio is 1:3. Voltage gain versus duty cycle graph. The blue color shows step-up converter combined buck-boost converter. Red color shows boosting converter with charge pump, and green color shows KY converter. Purple color proposed converter. This shows the simulating model of our project. The output of gate pulse. The output for coupled inductor waveform. The input and output voltages. The output voltage and current waveforms. Software requirements: MATLAB, MPLAB, Simulink. This is a picture of our hardware. This is an output of waveforms that we get from our project: gate pulses before amplification and gate pulses after amplification. Coupled inductor waveform for primary voltage and secondary voltage. Input and output voltage. Input voltage can be seen on the left side and the output voltage can be seen on the right side. This shows the hardware requirements. Applications: used in battery charger, used to operate DC brushless motor, used in telecom devices, medical equipment such as press release. Advantages: output voltage gain is high, output current is non-pulsating, reduced ripple in output voltage, number of switches is reduced. Conclusion: by the combination of KY converter and coupled inductor, voltage gain is increased. Voltage gain ratio is 1:5. It has no floating output. Output current is non-pulsating. The number of switches is reduced. Future scope: by varying the turns ratio, the voltage gain can be further increased. The MOSFET switch can be replaced by IGBT for swapped switching. Thank you.